The Universal Turing Machine is a fundamental theoretical model of computation. Some would call it the mother of all computers. And I will present the exploitation of a vulnerability that I've discovered in Marvin Minsky's 1967 implementation of the Universal Turing Machine. As an introduction to the actual exploit, I'll review how these Universal Turing Machines work. And then I aim also to conclude by some general speculations about whether this might say something about computer security in general.
Welcome to talk.cybercni.fr.
Welcome to Talk Cyber CNI today from Paris, and we had a little bit technical problems with the setup here. Also, the LinkedIn is not working today, so sorry for that. But in any case, we are very happy to be live. Talk Cyber CNI, the monthly speaker series today with the special edition with Pontus Johnson, and as usual, we have for the questions the Slido, and therefore, Alex, I hand over to you so that you can briefly explain how the Slido is working.
Okay, thank you, Mark Oliver. Thank you, everyone, for attending this presentation. You will be able to ask questions on the YouTube chat, of course, but you also have access to a tool called Slido, and the link is provided in the chat. With this tool, you will be able to ask questions, and after the presentation, maybe to answer a small word cloud. So thanks everyone for attending again this presentation. Back to you, Mark Oliver.
Perfect. Thanks a lot for the intro. So the reason for the special edition is that we're very happy to have today Pontus Johnson. You might have read about him because he created a wonderful paper about security risk or a security vulnerability that he found in the Universal Turing Machine from Marvin Minsky, as you heard in the introduction. And to give you a little bit backstory, I was getting in contact with him and discussing the idea of maybe presenting that, and I'm super happy that he agreed and that we have him today to present us what he found, which I personally find super remarkable and super interesting, because I cannot think of a better way of understanding how a buffer overflow works than the work of Pontus. And so I'm very happy he's here with us today. So who is Pontus? So Pontus Johnson is a professor at the KTH, Royal Institute of Technology in Stockholm, Sweden. His research interests mainly lie in the area of cybersecurity and the analysis of architectural models of computer networks. In particular, he's working on stimulating cyber attacks on such networks. Pontus supervises a number of PhD students and holds courses in ethical hacking. He's the director of the Center for Cyber Defense and Information Security at KTH, which is a collaboration with the Swedish Armed Forces. And on the website, you'll find some more details about his CV. And I can already say that also in the future, maybe there's another opportunity to exchange with him, because he's the perfect candidate for our series. So without further ado, Pontus, I hand over to you, and we are all very much looking forward to your talk.
Well, thank you, Mark Oliver, and thanks a lot for that very kind introduction. I'll be talking today about about hacking the Universal Turing Machine, and that's really not the main focus of my research or my academic activities. It was a kind of hobby project that I spent some time on quite some while ago. What then happened was that I thought that because I thought I found a vulnerability in this Turing Machine, I thought, well, I might as well get it registered in the international database for vulnerabilities. So I submitted. You can do that in 5 minutes. If you think you found a vulnerability, I submitted it to a database that's called the NVD. It's the National Vulnerability Database. It's American, but it's really international. And it was accepted. And when it was accepted there, all the vulnerabilities that they accept, they are disseminated to a Twitter feed, and people are looking through that at that Twitter feed for serious and interesting, obviously, also vulnerabilities. So this was picked up in the news media, and so the talk here that I'm giving, I have this title: Mutter alle Sicherheitslücken, Arbitrary Code Execution in the Universal Turing Machine. And this German one is from the article that you can see here in Heise. I thought there was such a funny title, so I felt I just had to reuse it. So what I want to do today is I want to talk a bit about, first, arbitrary code execution, what that is, and then I'd like to talk about the Universal Turing Machine, where it comes from, and then what it can be used for. And then I want to go into details, and there will be a quite detailed section on a specific Universal Turing Machine, the Marvin Minsky implementation, and how it works, and then how also it can be hacked to achieve arbitrary code execution, and what it means really to do that. And then after that, after being down in the weeds for a while, I hope we can abstract, take a step back, and consider whether there are any implications of this that matter, and what those would be in that case. All right, so let's start with arbitrary code execution. So you can see Elon Musk here. He says that engineering is the closest thing to magic that exists in the world. I think that arbitrary code execution is the closest thing to magic that exists in the world. There's something really remarkable about this thing, that you can, by some magic incantation, some specific string that you provide, you can execute your own code in a system where that was not at all intended. You can become a local god in that system. You gain enormous powers. And so for me, it seems like arbitrary code execution is really the pinnacle of hacking. It's the finest thing that you can do. And it's also a very remarkable and strange thing that this actually happens, that it's possible to do this. So I just want to put this, start with this, that arbitrary code execution, it's a particular kind of hacking, and it's really, I think, the most magical of ways. It's also remarkable that arbitrary code execution is prevalent. Here is a list of this is the common weakness enumeration. It's a list of the top 25 most dangerous software errors, and half of them can lead to arbitrary code execution. So it's not a fringe phenomenon. It's something that really that we really have to take seriously in cybersecurity. Here is an example of how arbitrary code execution can happen. This is SQL injection. SQL is a structured query language. That's how you talk to some databases. If you take a look at the logon screen in a web form, for instance, to the right here on the screen, there's a field called user ID, and then there's a password. For simplicity, in this case, the user ID will be a number. Now, that user ID, the text string that's written there, it's written as a text string. It will be translated in the program that receives the input from the logon screen into the text user ID here. And then the text user ID in this web system will be appended to an SQL statement, which looks like this. And an SQL statement is a string, and this string will be submitted to the database, and the database or the database management system will then interpret this and execute this. So here it says select star, which means everything, from the table that's called users in the database, where the user ID equals, and if your user ID is 105, and that's what you wrote, then what you're going to get back here in text SQL is the whole entry for your user, the 105, and then you can check with the passwords and so on that they match. Now, what a hacker can do here is to not provide just 105, but provide 105 semicolon drop table users. And the result will be this SQL statement, which is the same. Select everything from the table users where user ID equals 105, just like it should be. But then comes this semicolon. It shouldn't be there really, but the hacker added it. And then there's a new line which says drop table users, which means that you can then, that the SQL database will interpret this and will delete that table. And so this way, the attacker would have deleted the whole user part of the database, which of course is very unfortunate for the legitimate users of the system. This is a standard example of arbitrary code execution. We'll keep this in the back of our minds now. For now, we move to a different subject. Well, first, though, before we do that, the problem here, the problem with this program is that there is no input validation. So this is a weakness. This is a common weakness that you don't validate the input. You shouldn't allow the semicolon, for instance. You probably shouldn't allow anything but numbers here, so that you allow the string to be appended to this string. That's the problem. And so improper input validation, that is a vulnerability that is particularly relevant also in the rest of this talk. Now to something completely different, the Entscheidungsproblem. So for the computer scientists out there, the Entscheidungsproblem, or actually the mathematicians also, it was in the early 20th century. There was great hope that there would be a solid foundation for mathematics, and David Hilbert was the great proponent of that strive, that ambition to create this solid foundation. He postulated a number of problems or questions that had to be answered, and he was certain that they would be answered positively. And one of those was this Entscheidungsproblem, which is a decision problem. And as you can see here, it's a bit convoluted. Is there an algorithm that will take a formal language and a logical statement in that language and will output true or false, depending on the truth value of the statement? More or less, is there an algorithm that can, in any relevant, say, formalism that we're concerned with, that can tell whether a statement is true or false? Is it possible to say whether a statement is true or false? Is that always possible? So that's the Entscheidungsproblem. After some years, there was a paper by the great Alan Turing. This paper on computable numbers with an application to the Entscheidungsproblem. He addressed this problem. He realized that he could create a problem which reduces to the Entscheidungsproblem. He called it the halting problem, or it's called the halting problem. And it goes like this. From a description of an arbitrary computer program and an input, determine whether the program will finish running or continue to run forever. If it's possible to decide to create an algorithm to do this, well, then it's possible to solve the Entscheidungsproblem. But Turing, in this paper, he demonstrates that it is not possible. So that was a great discovery, and that put one more nail actually in the coffin of a solid foundation for mathematics. But while in the process of solving this or answering this Entscheidungsproblem, Alan Turing needed, as you can see here, from the description of an arbitrary computer, and in 1936 there were not many computers around, so he needed a computer, so he created one, and that's the Turing machine, and actually the Universal Turing Machine. So it's kind of a byproduct in this paper to the ambition of addressing the Entscheidungsproblem. So the Turing machine, we'll talk more about exactly how that works, but we can say that it was used for this Entscheidungsproblem, but it's also become very used in many other fields. So I went to Google Scholar, I checked this paper from 1936, and then I clicked on who cites this paper. And here's the list of the most cited papers that cite this paper. And at the top, you have Alan Turing himself with another paper, but then we have papers on deep neural networks, on quantum cryptography, on economics, on psychology, on the future, there's this famous book by Ray Kurzweil, The Singularity is Near. And there's on complex systems, algorithmic information theory, and quantum theory, and all kinds of theories. It turns out that this Turing machine, this very, very simple, the simplest of all, actually, models of a computer that is very useful. We have at the one of the final one here is the Marvin Minsky book, Computation. We'll get back to that. That's the implementation of the Universal Turing Machine that we will be addressing. And here's Stephen Wolfram also. He's also interested in Turing machines. We'll get back a little bit to him also. So these are legitimate uses of the Turing machine. There are less obvious things that people do with the Turing machine. One thing that you can do, which Claude Shannon spent some time working on, is to try to devise the smallest Turing machine possible. And the Turing machine, the size of a universal Turing machine should be determined in the number of states and its alphabet. And there are really small universal Turing machines. There's a problem called the busy beaver problem, which runs on a Turing machine. It's a really, really complicated problem with implications for complexity theory. But there's also just a record in trying to find the most successful busy beaver in a Turing machine of a certain size. You can do self-replicating Turing machines, and you can build Turing machines in Lego, and you can build Turing machines in wood, and you can build Turing machines in Minecraft also. You can have a Turing machine tattoo, as you can see here. You can do drawings with Turing machines, which is this gray-black thing in the corner. And I thought I'd show also another thing that you can do.
So the core of it is actually that you have this tape in the middle, and this is an infinitely long tape, and it could be infinitely long in both directions. So this could actually be made of chocolate, and I did come with stuff to make it out of chocolate, but the chocolate that I could get hold of, the actual squares were a little too small. So if you get larger bars of chocolate that are even larger than this, then you could actually make the whole thing out of chocolate. Well, I hope this looks a bit like a strip of chocolate though. The first problem you encounter is this tape does have to be infinitely long.
Right, so you can create a Turing machine out of chocolate also. So yet one thing that you can try to do with the Turing machine is to hack it, in particular then a universal Turing machine. But why would you want to do that? And for me, the reason why I went out on this hobby project, I started it, was because I've been thinking a little bit about the root of cybersecurity and insecurity. Why is it that computers so often are insecure? I mean, it's a huge societal problem, and it seems to me that it's not clear why this is the case. Why does it seem so very difficult to solve this problem? Why can't we build secure systems? So one way to address a problem is to try to solve it in the simplest form that you can. And then you have to pose it in the simplest possible form. And that's really what this project was about. What is the simplest way to understand what insecurity and hacking is? And that would be, I think, to hack a universal Turing machine, the simplest kind of computer possible. All right, so that's the background to why this might be interesting, and what the Turing machine, where the Turing machine comes from, and then also this issue of arbitrary code execution. Now we're going to get into the weeds of how Turing machines work. And this is here a diagram of a Turing machine. And so you can say that there is an infinite tape with that is divided into squares. And then there's a head. This is the M thing here, or the top part of the M, which can read the square that is positioned above, and it can write something to that. And then it can move one step to the left or one step to the right. That's a Turing machine. A tape and a head you can read, you can write, you can take a step to the left or a step to the right. And then there are many different Turing machines, and the different kinds of Turing machines, they're determined by when you decide to move left and right and what you decide to read or write. Should also mention that you can have any symbols in each square. You can have ones or zeros and zeros, or you can have A's and B's and whatever symbols you want. How this head moves about is determined by a state machine. Here we have a state machine, for instance, for a binary counter. This state machine will count a binary number and will increase it by 1 and continue to do so until infinity, or until the tape ends or the input ends. We will take a look at how this works and how this state machine functions here. So you see the tape. On the tape, we now have 4 numbers. They are the input to the tape. So this is the input to the Turing machine, this binary counter Turing machine. The head is located at the rightmost, in this case, on the 1. And you can see we are also in state Q00. And state Q00, we can see it in the diagram. That's this state here. So now we see that we are positioned above the 1. If we are positioned above the 1, that's what this means. In that case, we shall write a 1 in the same square, and then we shall go to the state Q1, and we shall take a step to the left. So we can try that. There. So we did that. We read the 1, we wrote the 1, so it's the same as it was. We moved to state Q1, which we are at here now, and that's it. Yeah, and we took a step to the left. So we're here now. Now we are here. We will see 0. Here's the 0. We're going to write a 1, and then we're going to go to state Q0 and take a step to the right instead. There, we did that. And then it proceeds like this. Here we will do the same thing actually. But so what we can also see here in this, for this to work as a binary counter, ignore this rightmost digit. It's going to be 1 all the time. This is the actual number. So we just counted 1. And if we continue now, we will see that there we have 2, 3, 4, and so on. So this is a very, very simple Turing machine, and it does this binary counting until you tell it to stop, more or less. All right. Remember also, this is the input. That's important because we will get back to that. Now, let's move on to a universal Turing machine. What's a universal Turing machine? Well, that's a Turing machine that simulates Turing machines. So here we have the universal Turing machine. It has a particular state machine here that allows it to simulate other Turing machines, like the binary counter. And there are some different universal Turing machines. For instance, the one that Alan Turing himself devised, actually that had some bugs and it was a bit convoluted, so it's not the easiest one to work with. Arguably, the easiest one to work with, at least that I have found, is the Marvin Minsky implementation from 1967. It's a pedagogical version, and it's a pretty convoluted, the Universal Turing Machine anyhow, so it's good that we don't take any one of the more convoluted ones. There are smaller ones than this that have fewer, here it is, that have fewer states and a smaller alphabet, but they become more difficult to understand. So here is the state machine. We'll go into that in detail. In addition to the state machine, we also have the tape of the Universal Turing Machine. So recall, the idea is that we want to simulate another Turing machine. So we're going to have this as an example of what we want to simulate. In order for this machine to simulate this machine, well, it's like a computer running a program. First, you have to specify what the program is. So this has to be written in the form of a program. And we will write that on the tape of U, and we will write it here. These are the quintuples. That's the description of the Turing machine. And then also we need to know here in what state this simulated machine, which we can call T, is in. So first it's in state Q00. And we will have the state here on the tape. And then there is input also for this Turing machine, and that input is infinite to the left. So in this case, infinity stretches to the left. That's still, it will become, you can simulate anything like this. And then this M here, that is the symbol for the head location of the head of this machine. But the problem with have an M here is that you don't see what symbol it's really located above. So we have that here instead. So in this case, it's located above the symbol 1. Then we will have a Y here, which separates the tape, the input and the tape of the Turing machine that is to be simulated. We have an X here before the description of the program. And now the program, it's supposed to describe this. It does that by describing each one of these transitions. So it does it, here is a description of one transition. If you're in the state Q00, this one, and you read a 0 here, then you should go back to Q00. So we're going back. You should write a 0 here, and then you should take a step to the right. And so there are 4 transitions here. There are 4 of these quintuples, as Minsky calls them. And because we want to have this program in only in binary format, we get rid of the Q here. And so we have 0, 0. And then we trade R and L, right and left, for 1 and 0. So for the first quintuple, for this transition, we will have 0, 0, 0, 0, 0, 0, 0, 0, 1. And that is located here on the tape. And this is then placed here. So that's the Turing machine as the Universal Turing Machine of Marvin Minsky. Now, because it's a bit a lot to take in, I have a simulation here of this machine. Let's see if I can go to that. Oops. There. So here it is. This is the Turing machine. The head is located here in the bold, large symbol. This is the head of the Universal Turing Machine. Here, as mentioned, is the head of the simulated Turing machine. And now we can take a step. We are located here. This is the starting point in state 6. And it says that if we read a 1, which we are reading right now, then we shall write a B. And we should go back to the same state and take a step to the left. So we can do that. Look, we did that. So the 1 was translated to a B, and then we took a step to the left. Now it says, well, if we read a 0, then we're going to write an A and go back here and take another step to the left. So now we have an A here. And you can note that there are B's and A's. This Minsky machine uses A's and B's as proxies for 0 and 1. It would be translating 0s to A's and B's to 1 back and forth, just in order to keep track of where it is in its execution. So every time you see an A, think 0. And every time you see a B, think 1. So we continue. Now it says 0. It's going to go do the same thing again. It creates an A after that. Now we get a Y. If this has a Y here, then we're going to jump over to stage 2 here. And we're going to write a Y also. Let's see. Step, yes. So and now we're moving right because there's an R here. We see an A. There's an A here. So we take a step and we end up here. Now here is an important thing. When we are here, you can see that we have specified what happens if you see a 0 and if you see a 1. But what we're looking at is an A. So what happens now is that there is an implicit quintuple that is very important in the Minsky implementation. The most common quintuples are not, there are no arrows here because it becomes very cluttered. So it's very simple to say that. So when you don't have an arrow here for a transition, what the machine is going to do is it's going to write the same thing as it wrote. It's going to go back to the state that it's in, and it's going to take a step as specified in the in the state symbol here to the right. So we take a step, you see, it doesn't touch this, it leaves it untouched. It stays in the same state, but it takes a step to the right. And that happens again now, and again. Now it sees a 0, and so here it takes a step and jumps over to the next state. So we took 9 steps. Now we're going to take hundreds of steps. And what we're going to do here is that we're going to go through 4 phases. The first, in order to simulate the binary counting. The first phase, it identifies what program quintuple, what program statement is going to be executed. So if you recall, the M here was standing on top of the letter 1, the symbol 1. And in the binary state machine, if that is the case, then this is the transition. You're standing in the transition in the state 0, 0 in the binary machine. You're looking at the 1. What you want to do now is you want to go to the state 0, 1. You want to write the 1, and then you want to take a step to the left. That's what this means. So this machine now, the universal machine, needs to identify that this is actually the program, the quintuple, the program statement that we want to execute. So it's going to first trying to find it, and it's looking first at the first one. It doesn't find it, and then so then it marks it like this with A's and B's. That indicates that, okay, I've seen that one now. Now it's going to try to find it here, and it will find it this time. So it's moving, it sees a 0, good, and here's a 0, good, and now it's going to match the B here with the 1 here, and that's also right. So now it's found the proper quintuple that it will execute. Now in the next state, what it's going to do is it's going to take this second part of the quintuple. What am I going to do? It identified already. I was here. I read at the state 0, 0. I read a 1. I want to go to state 0, 1 now, and I'm going to write the 1. So it's going to take this and it's going to copy it into this location in the Universal Turing Machine. Recall, this location is where it's at right now. So it's at location at state 0, and it's seeing a 1. Now in the next, after it's completed this this iteration, it's going to be in state 0, 1. So we want to have state 0, 1 here, and it's going to still have the 1 there. So we can play this now and let it perform that. You can see now that it's in phase there. Whoops, we went a little bit too fast. That in the second phase there, now we are completed in copying here. We just copied the next instruction. Now what we want to do is we actually want to write something here under the head of the simulated machine. And so if I move a little bit quickly here, we just move to the next phase. I click the next phase button, and we don't have to take all the steps individually. You see, now we wrote something here, and now we want to move the head 1 step here. The M is going to move here because that's what the binary counter wants to do. It wants to move a step to the left. And there it did that. Okay, so if we play this now fast, you will see that it's mostly occupied with trying to find what statements it should execute, what quintuples are relevant, and to copy that into its own state. But occasionally it wanders out here to the tape of the simulated machine and actually performs this binary counting. So you can see here that it's slowly counting up. So you have a 1 here now. That's it didn't have that before, and so it goes. Okay, so this is a crash course in how universal Turing machines work. I hope that you are approximately with me still. We'll get back to this, so this is how the Minsky universal Turing machine works. Now, what we wanted to do was to hack it. And if you want to hack something, you first have to find a vulnerability. And I think here that I found one when it, and that is in these, you can see this statement here, the most common quintuples of the form where you start in one state and then you move back to the same state and you write the same symbol, they are simply omitted. So those are these 140 arrows in the diagram, transitions that Minsky did not explicitly draw, but had implicitly instead. And those are necessary. 70 of those, I have come to the conclusion, are necessary for this machine to work. But this blanket rule, it creates another 70 that are not really necessary. They don't do any harm normally. They're just not used. But what they result in is improper input validation, because it becomes possible now for an attacker like myself to add symbols to the input that Minsky never considered. So for instance, I can, let's see, yes, I can, here is a new tape. This is the same binary counter, but all I did here is that I added an A here on the input. And if I add an A to the input here, you're not supposed to do that, but the Minsky machine will accept it. And you can see if we now move quickly here from, we search for the right instruction for the first state transition. Now we're going to move the, we're going to write something under the A, under the M. Now we're going to write the M. The M should be written here because the M was here. That's the tape head. The tape head can move only one step, so it should only be able to move here or here. But because I wrote an A here, what happens if we step through this is that when it arrives at here at this A, it does what it should do. It's in this state, state 23. It sees an A, it writes a 1. And then when it gets here, it's supposed to write an M because it's expecting a 0 or a 1, and now it's supposed to write an M. This means that it has moved the head of the simulated machine one step to the left, but it sees an A instead. Because it sees this A, it falls back on these implicit quintuples. So what it will do, we will simply write an A in the same place, so it won't touch it, and it will take a step to the left. So you see it takes a step to the left. And now it's in the same position, and now it's going to write the M. So all that happened was that the M was supposed to be written here, but it was written there. And actually, this little hiccup, it's just like a stutter. If we play this now, it won't matter. It will kind of recuperate from this small error, and you can see that the A is gone, and now it's just doing the binary counting again. So just writing some random symbols there, it may have an effect and may not. Now, to hack this now, that means the following. I remind you of the SQL injection. The input, that's where you write the malicious stuff. And it gets in this SQL statement, it gets added here. So in arbitrary code execution, you kind of write your program in a place where you're supposed to write data. And so it's the same thing that we want to do here. This is the place for the data to the binary counter. And here is where we then have as a, this is the input. So this is what we have to play with as a hacker. So we're not allowed to modify the binary program and not the state or anything like that. We can only modify the input. And so is there anything that we can write here that can achieve arbitrary code execution? That's the question. And so what we want to do is the following. We have this tape, we have this input, and we're running this machine, but we want to end up in this tape, which is our own machine. And this, of course, because we are hackers, this is an eraser. It will erase everything. It's like drop table, but on a Turing machine. So what it's going to do is, independent on if it sees a 1 or a 0, it's just going to write a 0, take a step to the left, and then it's going to write a 0 and take a step to the left. So it's just going to erase the whole tape. That's what we want to achieve. So is there anything we can write here that makes the machine, the Universal Turing Machine, execute this? So we have to get this onto the tape, and then we also have to make sure that the Universal Turing Machine, the head is located in the right position, and that it is in the right, the Universal Turing Machine is in the starting state. If we can achieve all of that, then it will execute this program instead of this program. Okay. So we could brute force this. We could try just all the strings possible for this here. We could try all strings and see if we randomly happen upon this particular one. This is really, really difficult. For one thing, it is there are 8 symbols, and the string is the number of permutations here is 8 to the power of n, which is with the exploit that I will show you later, 8 to the power of 28. That's just too big to brute force. And for the computer scientists here, we can also speculate about whether hacking in this sense, if it's what the computational complexity of this problem is. But I won't go into that. Instead, in order to find that magical string that we place here, in order to find that without brute forcing, we need some inspiration. And the inspiration that I employed was from another kind of arbitrary code execution vulnerability that's common, which is the stack buffer overflow. When you write the program in, for instance, C, you can have functions. When that program is executing, the functions will be represented as a stack frame. So it's a memory, a piece of memory. It's called a stack frame. And here you will have local variables and these buffers here. You will also, because you're in a function, you need to know how to get back from that function to the calling function. And therefore, the return pointer is written here in the stack. And there's some other stuff here also. Now, if there is a buffer overflow vulnerability in a program, that means that this buffer or this buffer can be overwritten. It can become too long, and there's no input validation. So it is allowed that it becomes too long. If this becomes too long, then it will write over the return pointer. And so here is a smashed stack, as it's called, where the attacker has written over the return pointer and written the attacker's own return or pointer. And now when the program counter reaches this and wants to return, there's another pointer here. And that doesn't point back to the calling function anymore. This new pointer, it calls right into this buffer. And in that buffer is located malicious code that the attacker added. So this is a buffer overflow. And so the trick is that you kind of include the code that you want to execute. You include it in the data, because it's, as an attacker, this buffer, you fill it, it's typically data that maybe you filled into some dialogue form or some user data. Okay, so that's the inspiration. So I was thinking that, well, as I said, we have this program, the binary counter. We have this that we want to fill with something, and we want to achieve this program. How about we simply write the program that we want to have, in the data section. So we just take this, what we want to have, and we just write it here. How would that work? We can try that. So we go to the simulator, and we now move to this let's see here. There. So here we are at the naive exploit attempt. So here is our program that we want to have executed, but we put it in the data section. And the machine, the Universal Turing Machine, it's in state 6. It's located with a tape head here in this machine condition, which is where it should be. And if we start playing this, we will see that we won't achieve any arbitrary code execution. As you can see, it's executing these statements. That's where it's spending all the time. And it's moving this head as it did before. It will be a little bit confused because there's a Y here, but that just creates a stutter, and it will continue with its binary counting as best it can, given that there's a Y there. But it will just continue doing binary counting over here. It's not going to execute any code that I wrote here. It's just going to change that code that I wrote there into something which is illegitimate, well, something meaningless probably. It's going to do binary counting on my code. So that doesn't work. We cannot simply write the exploit in the data section. So I spent quite some time trial and error, and then I came up with something that looks like this instead. So here is the working exploit. And so one of the important things is that I had to change the 0s and 1s to A's and B's. If I do that, then that will trick the machine in important ways. I also had to remove some symbols at the end that were not really necessary of the original program. I had to add some other symbols here and here. And having done all these things, I actually achieved this arbitrary code execution. And we can now see how that works. So now here is the malicious tape and the malicious input. So we are standing here. This is the binary counter as always. And here is the head of the simulated tape. But here now is my malicious program. And here is the input to that program there. So my malicious, I just wrote this here. And we can see, so I have executed the Universal Turing Machine on this tape many times, and I can tell you that nothing particular happens in the first 3 phases. So we can just rapidly jump through them. The first phase identifies which of the binary counter quintuples we want to execute. The second one does the copying into the machine state here, there. The third phase writes, well, here's the M. Now it's going to write an A there. That's just as it should be, completely legitimate. Now, what it's going to do, what it wants to do is it wants to place the M, which represents the Turing, the simulated machine's head, it should place it here on the S. But as we saw previously, when it gets to that point, first it changes this A to a 1, which it should do. And now it's looking for a 0 or a 1, just like we had previously. It sees not a 0 and a 1, so it takes a step. And now it sees an A, it takes another step. And so what happens here is the really critical part, that it kind of just slides all the way over here to this one. And now finally it sees a 0 and a 1. So what happens here is that we're in a really weird state in the original or in the simulated machine. The binary machine is not, the binary counter is not supposed to be able to move the tape head here, because when it gets here now, we take another step, it places the M here. So the M jumped from here, this one, it was where it was at, over here. That should not be possible. That's like impossible. But that's what happened here. So now we are in a weird state, but this does not mean that that the attacker controls anything here. So now we take, say, a few more steps, and we see that we're waiting for the S here. That's because we want to get back here to the machine condition of the original program. But I place this malicious S here. So eventually, when we get to that point, it stops early. So it stops already here. That's important, so that it doesn't go back to the original program. And then it ends up in the starting state. But now it's in a weird state, because when you're here in the starting state, you should really be here. You should be standing above this symbol or this symbol. I don't remember, one of these. But we are here. I would like, as an attacker, to be here in my machine condition. This is the machine condition of my program. I would like to be here, but we're not anywhere. So we're in the middle. So fortunately, if we simply step through this, the first thing it would actually walk up to my machine condition, and now it's going to try to find my the first statement in my code, but because it sees only A's and B's here, it doesn't find anything. So it goes and it finds some kind of random stuff down here. This is just a buffer that it finds. So now it goes through a whole cycle of execution, doing more or less useless work for both me and for the original program designer of the binary counter. But eventually it gets back here, and here comes soon the magic part where my A's and B's that I've written here are now magically transformed here into ones and zeros. This is a cleanup operation that's supposed to do. But look, now we are really very close to what I would like to have, namely state. Yeah, so now we are there. Here, we are in state 6, the starting state, but we are in my machine condition where I want the head to be. And here we have my program. It's formatted perfectly in zeros and ones, just like I wanted it to be as an attacker. And here is the resulting tape then of my machine. And so now if we play this, it will never return to the original program. It's going to execute my program instead. So if we play this, you can see that that's exactly what it does. And this tape here, it's going to erase the ones here and turn them into zeros, and eventually turning all of this into, well, erasing the whole input to that. So that's it. That's the arbitrary code execution in the Marvin Minsky implementation of the Universal Turing Machine. I'm imagining that for most people, it should probably be quite difficult to follow in everything of this. I tried to make this as pedagogical as I can, but it is a lot of stuff. But I hope that maybe at least you caught the greater scheme here. And so what we can see then from this is that it is possible to achieve this arbitrary code execution on the Turing machine, the Universal Turing Machine. And then we can consider, if we want to mitigate this, if we would like to prevent this, how would we go about it? And there are some things that you can do. Recall that we have improper input validation. That's the main flaw in many different programs, and that causes vulnerabilities. And here it's the same. So we could validate the inputs. We could do that by having another Turing machine, like we append it to the Universal Turing Machine that makes sure that we only get the proper input. Of course, that will add complexity to the machine, which is not going to be as simple as the Marvin Minsky machine, because we need this added layer of security. Another thing that we could do would be to, as you recall, the vulnerability is based on, at least partially, on these implicit quintuples, these transitions between from the same state to the same state. That Minsky defined as a kind of blanket. So there were 140 of those, but only 70 are needed. So we could draw 70 more arrows in this diagram. I think there are 45 transitions here. We could draw 70 more and then only allow those. That would prevent my exploit from working. So that, but that also is, I mean, that adds another kind of complexity. I mean, in the specification of the machine becomes more complex. We could possibly use a special alphabet for T's tape. Now we're using zeros and ones, and we also have zeros and ones for the program. So it's easy to become confused here. But it may or may not work to do that. Another final thing that I've thought of that one could do is that there are some specific parameters that you can use here, for instance, between the M and the Y, between the head of the starting position of the head of the simulated machine and the end of the tape of the simulated machine. Here we have 3 zeros. According to Minsky, you can have any arbitrary number. If we have 3 or 4 or 5 or 6 or a million, my exploit works. But if we have 1 or 2, my exploit doesn't work. Maybe there's another exploit that does work, I don't know, but mine doesn't. So maybe it's possible to find some specific parameters that make this machine unexploitable. That could be. Okay, now I would like to step back. So this was, feels to me, a very rapid attempt to explain the details of this arbitrary code execution of this Minsky implementation of the Universal Turing Machine. So if we return to the question of why computers so often are insecure, it seems to me that might be related to this, to me, really surprising discovery that even the simplest imaginable computer is vulnerable to this rather complicated and rather magical kind of attack. Why is that? Why is it that this machine is vulnerable in this fashion? And so a hypothesis is that, is it the case that computers in general, that they are intrinsically brittle, that at their very core they have this propensity, like a trait that they really want to, that propensity that they're leaning towards, that they really want to have arbitrary code execution vulnerabilities, that it's in their nature to have arbitrary code execution vulnerabilities. They don't necessarily have to have it, but they are perhaps likely to have it. I mean, is that the case, that there's some kind of intrinsic brittleness? So that's a question that one might ask. Well, one can consider then what the root causes of insecurity might be, and there are a number of hypotheses that many of you have surely heard about previously also. One, for instance, the grand old man of computer security, Bruce Schneier, says that complexity is the enemy of security. And it is true that very often systems become insecure because they are very complex. But here we have the least complex machine possible. You cannot have a less complex computer, but it's still vulnerable. And so to me, it seems like complexity cannot be the only answer, at least, to why we find these problems. Another hypothesis was just human fallibility. Humans make mistakes. That's why we have vulnerabilities. And that's also, I think, true, that almost every time there's a vulnerability, there was somebody who forgot to do something or messed up somehow. And you can easily patch almost all vulnerabilities by just fixing the problem that some human caused. And in this case, you could say, well, Minsky, he caused the problem here because he didn't consider security. Of course, he was completely uninterested in security when he created this machine. But to me, it's weird that he was totally uninterested in security when he created this machine, but he happened to create the vulnerable machine. I mean, he could have happened to create a secure machine, but that didn't happen. It happened to be vulnerable. So this is for the propensity hypothesis, that it kind of it easily happens. Another hypothesis is the John von Neumann stored program architecture, that the program and the data is stored on in the same memory, causes confusion. And in this Turing machine, they're stored on the same tape. That causes confusion. The Minsky machine becomes confused. It thinks that the data is the program, and that's a cause of the problem. So there are other architectures like the Harvard architecture where the program and the data are stored in different memories. And maybe that could be some kind of solution. But still, if you want to have a computer in any meaningful way, you will have to be able to update and rewrite the code in the program memory. And then you kind of fall back into the same problem again. There's also the concept of weird machines. The paper that's cited at the bottom here, there's Thomas Dahlian, and there's also Sergei Baratus, people who have been talking for a long time about the concept of weird machines. And we really see weird machines in action here. When you are at this, in this machine, at a certain point, there is this weird, unexpected input, and you end up in a strange state that is not possible really to represent in a state diagram at the simulated level anymore. Like the head of the machine jumps 20 steps to the left. That's not supposed to be possible in this in a state machine like this. But then it's possible to kind of bring it back into a sane state in this case, and it will continue executing in this instead. And so I'm not sure whether weird machines can explain insecurity, but there is it can I think explain at least or formalize exploitation in a certain sense. So I'm thinking that there's one other perspective on arbitrary code execution hacking, and maybe we can generalize it to hacking. It would be nice, but let's stick to arbitrary code execution hacking, because that is the discovery. So a hacker discovers that the Turing machine T, the binary counter, simulated on U, the Universal Turing Machine, we discover as a hacker that that Turing machine T is in itself is in fact also a Universal Turing Machine, so that we can run yet another program on that. So it's a Turing machine that simulates a Turing machine that simulates a Turing machine. And so what happens is this program is accidentally Turing complete. It was not intended to be. And the concept of accidental Turing completeness, that is not a new concept. There are other things that are accidentally Turing complete. We saw that you can create Turing machines in Lego and Minecraft, and in the x86 computer architecture, there's the mov instruction, move, that it alone is sufficient to perform any kind of computation. So it's Turing complete. It turns out that musical notation can also be Turing complete. And there's this card game, which is called Magic the Gathering, that I have never played, but that also turns out to be Turing complete. So there's a paper on that you can see at the bottom there. And of course, there are these smallest Turing machines that Claude Shannon was interested in, and also Stephen Wolfram has been recently interested in the smallest Turing machine. He came up with the idea of, well, a suggested smallest Turing machine of, I think it was maybe 2 states and 3 symbols, or 3 symbols and 2 states. That's a bit contested whether that really is Turing complete, but that you can create these very small Turing machines. It also speaks to that, and that these things accidentally become Turing complete. It's not so unlikely that things become Turing complete, and so that's why the concept of accidental Turing completeness is. And so then to conclude, perhaps it is the case that computers are intrinsically brittle, that they have this propensity for arbitrary code execution because accidental Turing completeness is common. It's not so hard for that to happen. It can happen quite easily, in fact, and given in particular, perhaps it seems if you're simulating on a Universal Turing Machine, it becomes even more likely. So I will leave you with this very hypothetical conclusion, and I think I will end there. Thank you.
Great. Thank you so much. I clap my hands already for the audience that is not visible to us here. So you made it quite difficult to ask questions because you covered so many aspects already in the talk. So very good. So you were perfectly prepared. Thank you for that. So let me start with the provocative question. You partly talked about it already, but maybe you can say a little bit more about it. So what the heck motivated you to do this research, or to ask a little bit more defined? What I really want to know is, like, what was your goal? Was it like you wanted to create a piece of art? You wanted to have a philosophical discussion? You wanted to educate people? Maybe you can say something to that direction?
It was actually, I would say it was personal curiosity that drove me to this, and I think that from my own perspective, as I mentioned initially, I have had also I have been thinking about why it is that security is such an issue, and it's been really difficult for me to understand why we can't build secure systems. What is it fundamentally that is the reason for that? And so, I think that was one thing that was kind of lying around the back of my head, and then. In computer science, you stumble across the Turing machine every now and then. And so these two concepts, I guess they just coincided in my head at some point. And at the same time that I had some spare time, because this was really just a hobby project for myself, and it is divorced from my actual ordinary research work.
Very good, very good. So yeah, maybe Alex, I hand over to you for the first audience question.
Okay, there are some questions. Thank you for the presentation, which was very interesting, Pontus. So there were a few questions. I will try, as usual, to group them by theme. So I will first begin with more global questions to begin easily. So Marsupilami had few questions, and the first one was, what inspired you to do this research?
Yeah, well, that's pretty much the question that I answered previously, I think. I was inspired by I think mainly the question of why, what is the root cause of security or insecurity?
Okay, and so other questions related to your work. What can today's software developers learn from your work, and how can your work be included in teaching?
Yes, well, those are questions that I have not really had well, I have not really considered. Well, I think that in computer science, actually, I had a guy, Andreas Rosek, who contacted me after this ended up in the paper or in the news, and he wanted to replicate this hack, but on his own implementation or another implementation of the Turing machine. And so we had some very intense back and forth to try to make sure that, because he didn't succeed initially, and so I thought, whoa, what if I made some mistakes somewhere? But fortunately, it turned out that there were no mistakes, and instead it's been replicated. But he wanted to use it in education because he's teaching Turing machines, and he thought that it was really interesting that this phenomenon exists in those Turing machines, or can exist. So I guess you can use it like that. Personally, I think that the philosophical dimensions to it are the ones that trigger me the most, and I don't think I'm done yet with thinking about this. Like I had this slide on NP, the NP hardness of hacking. Maybe there's something there. I don't know. But I'm a bit explorative, I must say, about what the potential real-world implications of this might be, or the consequences, or if there are any useful things that one can actually take away from this. There was in the very brief statement that was propagated with the vulnerability disclosure in all these channels where all official vulnerabilities end up. The people at Mutter who at the vulnerability database, they had added, the author states that there are no real world implications of this vulnerability, which of course, as compared to a vulnerability in the SMB service of Microsoft, there are really none here. So maybe there are none. I don't know, but maybe there are.
Okay, thank you for your answers.
So let me maybe jump in here. So because when we got in contact, we discussed a little bit of that also, and I told you, like, I love the work because it's really pure pure approach for teaching, because it's also the simplest or well able to understand computer where you show this vulnerability. So great. So therefore, for me, the answer is it has clear value and it has great value. And especially in this teaching direction, I think this will be a great idea to explore it further. But let me jump in the question. You would talk a little bit about the process. So can you give some more details about how does one start? So you have a Turing machine and you know that there are like buffer overflows and this kind of vulnerability from modern computer architectures. So what was your process of going through it? How long did it take? What were the step backs where you tried something and it didn't work at all? So could you share a little bit something about that?
Yes. Well, I think because I'm teaching ethical hacking. So that's also very important, I think, say, inspiration for this, that I have been looking at many exploits of many different systems. And some are really fascinating and some are quite trivial. But as security people do, you get to know all these kinds of strategies for exploiting things. And there's really a quite large gallery of kinds of, that's also a reason for why it seems to me that there must be something more fundamental, because there are all kinds of different vulnerabilities. There are cross-site scripting vulnerabilities, and there are buffer overflow vulnerabilities, and there are cross-site request forgeries and server-side request forgeries, and there's an endless list of vulnerabilities. There seems to be no, theory at all. No structure to it at all. But when you learn about all this, you kind of get a feeling for these how vulnerabilities can be exploited. And so I think that I had that helped me in considering how exploitation could possibly happen. And then I guess that I realized that the machine will actually interpret symbols other than zeros and ones. That was a really important milestone for me. That it will, and that it's also that it should. I mean, that's how it's built. It's built to interpret other symbols. You will have A's and B's even out on the tape of the simulated machine. It's just that the user is not supposed to write those symbols there. It's the machine that's supposed to write those symbols, but the machine will actually accept them. And so when I realized that felt very much like other exploits, that and improper input validation. And then I spent a lot of time in trying to coerce this machine into to executing my program. It was easy to get it to skip a beat, to stutter a little bit. But to get it to execute my own program, that was a lot of trial and error. I got it halfway, but then it slipped back into the old program, and all was lost. And so I had to try many different exploits attempts before I succeeded with the one that I found eventually. And I did this over a year ago, and then I submitted this as a paper to what was that? Well, I had a long discussion actually with the editor of the Usenix Login magazine. He decided he didn't want to publish this because he couldn't see that there was any news value in it. And then I submitted it to a conference. I got some really positive feedback, because before that I felt that, well, is this something or is this nothing? I got some really positive feedback there, but they felt that there's no real world implication, so they rejected the paper. And then that's when I submitted it to the CV database, and then suddenly it ended up in the newspapers. So that was the process.
Very good, very good. And I really love this, because it's very good also for the people that are doing security research, just to see it's not bam and there it is, but it's always a little bit like a capture the flag now with just the machine, that you do something, you look at what happens. So it's really something that one can really explore. And this is also what I loved about your presentation with the Turing machine, where you could see the steps and everything is obvious because you can see it, but at the same time, it's super tricky to then end up with a real code. And I can just imagine a bit how joyful you would have felt probably when you then finally had it and then it was working, and then you saw that you can even stack it and so on. And so, yeah, very nice, very good. You also talked about the protection. So if Alex permits me, I will also ask this question there. So in modern computer architectures like the Intel processors, a mitigation of such problems with the memory, you talk about the von Neumann architecture, is that you protect parts of the memory. So you say, okay, this is just not executable. Could you draw a little bit the relation to that? Would that be the solution to go for it if you would now be Minsky and say like, okay, I ship millions of these Turing machines, how can I mitigate from it, or what would you propose him?
Yeah, I mean, that's a good idea. That's also a perfectly good mitigation that's implemented in most systems, that you specify that you cannot execute code located in this part of the memory. And of course, and that would work here. It would prevent my exploit. What the attacker response is to this defense is called return-oriented programming. And what it does then is that it, instead of executing anything, it just makes sure to send the program pointer into existing code, maybe in the libc or somewhere where there's a lot of code. And it finds a little bit of code here and a little bit of code there, and it executes that. And then it jumps back into the attacker's control, and the attacker sends it away to execute another little piece. These are called gadgets. And I've actually been thinking about, is it possible to do return-oriented programming on the Universal Turing Machine? And I'm not, it could be that you could actually, that you could trick the program into executing, or the Universal Turing Machine into executing program statements from the binary counter. And then if you have a longer program than the binary counter, you will have more to choose from. And then return back to the attacker control. And then the attacker could choose which of the statements would be executed. I tried briefly, I have not succeeded with that, but maybe it's possible.
Good, very good. So I hand back to Alex for the next question from the audience. Thank you.
Okay, so I will go to the Renzo's remarks and comments on the YouTube chat. There were about 2 points, about 2 subjects. The first one is maybe the fact that the Turing machine programming is using a meta logic because you have a logic on your system and you have the logic of the behavior of your system. So when you mix these 2 languages, maybe this is the way that weird 6 happens, as says Renzo, for the fact that we we do not reason with the same logic while doing things with the Turing machine and when programming it, if I will say. And another quite interesting attack, I think Renzo has pointed out, which is linked to a question from an anonymous visitor, I would say, or listener, is that denial of services, infinite stutter, is maybe a valid attack. And the question was about the fact that how do you implement an action that stops a Turing machine?
So you can do a denial of service attack, right? And an infinite stutter, that would be if you just have a long list of A's in the input, then it would just keep stuttering. But if you could bring, so this particular binary counter doesn't have a halting state. If you could bring it to a halting state, well, if you as an attacker could coerce it into a halting state, that would be a good denial of service attack, I suppose. But that would depend on the program that is being simulated. Yeah.
Okay, thank you. So the other questions from Marsupilami. So I will take the one about your latest slides about what does a Turing complete mean and how does a cardboard card game to be Turing complete?
Yes, actually, I haven't read the paper about Magic the Gathering, how that is Turing complete. But Turing complete, of course, it means that you can that it is as powerful as a Turing machine. So Magic the Gathering, if you, I guess, the way I'm imagining that it works is that you move the cards around in a fashion that specified by the rules of the game. And if you then interpret the cards in the proper way, then you can do the same kind of computation that the Turing machine can. But I haven't read that paper. But actually, now that you mention it, maybe I should.
As far as I remember, some news from video games or games magazines, they created a state of games because it's a multiplayer game when, of course, each actions could be created as a Turing machine. So the game could play by itself for like making a binary counter or something like that by using some characteristic or specific cards and the rules of the game. But it's very, I haven't read it either. Okay, and so I have two more precise questions. The first one is more technical, but maybe you have answered it during your presentation. Does your exploit to Minsky's Universal Turing Machine allows to execute arbitrary code or only some code, a subset of all or unknown?
Arbitrary code. So you can, so I use this eraser program now. It's just a simple program with 2 transitions, but you can have an arbitrary length of the program specification in the exploit. So that can be well, arbitrary, yes. So you can, so it is arbitrary code execution, not just execution of the eraser program, yes.
Okay, thank you. And the last question from Marsupilami again. I don't know in what is in his mind, what he has in mind while posting it, but how did your colleagues react when you told them what you are working on?
Yes, well, they reacted differently. Some reacted, I would say, you know, with kind disinterest, uninterest. Oh, that's interesting, they said. Hacking the Universal Turing Machine. Okay. There was some people who were quite enthusiastic about it, but they were fewer than the ones who and in particular before it made the news. I think it's very difficult. You know, I'm saying that I'm trying to understand even what I'm talking about. If I, you know, in a conversation by the coffee machine or the virtual coffee machine as it is now, I say I'm working on a project where I'm hacking the Universal Turing Machine. Most people, I mean, if someone said that to me, I wouldn't understand what they meant unless I had, you know, performed this particular problem, this exercise. So I think that the reactions are quite natural. You have to really think about it before you understand even what it would mean to hack a Turing machine.
Okay, so thank you for your answers. I have no questions left. So back to you, Mark Oliver.
So yeah, I have a few more questions. The first question is bringing us back a little bit to the initial discussion and the first question that Alex was asking towards this teaching. So could, or better, should Minsky have foreseen this problem? And the question, of course, is behind this: do we have does this relate to potential fundamental problems in our software engineering or hardware engineering courses that we are teaching at universities? And also behind, like, is there enough relevance or importance in the curriculum today for cybersecurity? Do you foresee this to change in the upcoming years?
Well, some different comments on that. Firstly, Minsky, of course, he was not interested in security at all when he wrote his book. So, but then, as I said, that he happened to create a vulnerable machine. I think that's fascinating. I think that I think that it is interesting to have that this aspect is a part of when you read about or learn about the Minsky implementation of the machine. It seems to me that this is a quite interesting kind of added dimension to it. The extent to which it affects the curriculum, so you can have it in the curriculum of when you're teaching formal languages and automata and Turing machines. In software engineering, I think, and in security, I think this is a very, of course, I think this vulnerability has all of the hallmarks of the vulnerabilities that that we see in real life. That's I think maybe the most surprising to me now post factum when I observe this vulnerability, that it's very, very similar to the vulnerabilities, and it's due to the same reasons, and it's very analogous, and so that to me seems important, that it makes this more important and perhaps more useful as a guide to help us think about security, trying to remove the unnecessary clutter of a whole computer with spectrum meltdown vulnerabilities and infinite complexity of hardware and so on. So maybe there's something there that can be relevant for the curriculum when it comes to cyber security, for instance.
So we are doing a lot of MOOCs, so massive open online courses, and just hearing what you're talking about, and also from the question round. So the buffer overflow is like kind of the like a basic exploit that is used for spawning many different other exploits. And I'm just brainstorming a little bit, because what I could imagine what could be a really cool MOOC would be to start with the Turing machine concept, introducing that, and then afterwards doing your buffer overflow, and then introducing other concepts like ransomware. So imagine you have the event of the machine, and then it's writing, okay, please send bitcoins to something. This would be really cool, like from a teaching perspective. So I think people would really love that.
I think there are many things. I mean, of course, it is of course the case that you can implement everything on a Turing machine. But there's another thing I've been thinking about, is that one thing that is not captured in this there is the issue of access control, that which is so fundamental in computer security, that there are some things which should be allowed and some things which should not be allowed. And so gaining arbitrary code execution is not the same thing. I mean, it's not the same thing as root access to a machine, because arbitrary code execution, you can have that in the browser, and you're supposed to have it as a server in the browser even. But that's not God mode. God mode is root. And so, but it seems it would also be possible to incorporate, quite simply perhaps even, access control in this very, very simple computer. You could have multiple tapes, for instance, and one tape is for where you can for doing the privilege stuff. And then the question is whether you can escalate by, if you can have access to one tape, can you then gain access to the other tape? So. But I mean, of course, it should be possible to simulate everything on a Turing machine. So it's not surprising really that you could have arbitrary complexity of vulnerabilities and so on. But if it really becomes more pedagogical, that's the question, perhaps.
Yeah. So if you ever think about doing it, I would be happy to collaborate with you on it, because I could really think that this is like a different access to the matter that we are teaching on everyday basis. Because when I tell someone, okay, this is ransomware, this is a buffer overflow, it's kind of an abstract concept, because it's always like, yeah, okay, so you can overwrite the memory, and to do it, it's quite complex. And the other thing is really like the easy machine, and you can really explore the things. So yeah, Great, cool. As you are also a cybersecurity researcher, and this also is cybersecurity, but you said also you do other stuff. I will have to ask you also the obligatory question that I always have for the experts. So what would you say is the biggest cybersecurity threat that we have today?
The biggest cybersecurity threat?
Yes.
Well, I think that the biggest problem that we have is that we are unable to build secure computer systems. It seems completely impossible for us to do that. Even the most critical issues are the most critical functions. We discover vulnerabilities in crypto libraries. You should not have vulnerabilities in crypto libraries, and people are really trying to not have that, but we do. In operating systems that on which life depends, you should not have critical vulnerabilities, but we have them monthly and by the dozens. We have even started reading reports that there is worry about the cyber threat to nuclear weapon systems. It seems to me that those systems should be secure, at least of all the systems. But no, it doesn't seem that they are either. So because we're fundamentally not capable of building secure systems, and that's to me that's the big risk. Combined, of course, with the immense utility of computers, and that the universal machine, a machine that can do anything, it turns out to be super useful, and that means that we are digitizing everything that we can at an astounding pace. We're turning over everything that we can to the computers, and we leave it to their custody. All the global financial system, critical infrastructure of society, our lives when we let them drive our driverless or even current day cars, medical machinery, everything. So I say that those are the two things maybe that the Turing machine is, or that the computers seem so hard to build securely, or computer programs, and that but at the same time are so very, very useful.
Very good, and that's also a very good closing remark, because it shows that our series is super important, because there's so much more to explore and there's so much awareness to raise. And Pontus, thank you once again so much for the talk, because it was rising the awareness, and it was on the one hand super philosophical and like away from the basics, because there was so many concepts that we've seen, and on the other hand everybody could follow it either during the talk if you ever worked with a Turing machine, or if not, you can just follow the links that Pontus was using, and then you can replicate what he was doing on live. And so yeah, we cordially invite you to do this after the talk. So yeah, thank you very much. I clap my hands once again for this great talk. So thank you very much for that. For all the people in the, and also thank you, of course, to the team, so to Alex, to Renzo, to Olivia that did the back office work today with the chats and the communication. If you didn't subscribe to the channel yet, please do so. You can also subscribe on the website to receive always the announcements. The next edition will be, as usual, on the last Wednesday of the month at 5 o'clock Central European time. So the next talk will be by Michel Pabo, and he will tell us something about quantum computing. Those in the stream, the trailer will show up next. So we hope to see you again in about 2 weeks for the regular edition at the 30th of June at 5 o'clock. Thank you very much. Have a great evening, and subscribe to the newsletters and the channel.
A growing issue is the security of communication in general. And one of the threats right now is quantum computing. There's a lot of uncertainties about the strength of protocols with respect to the capabilities of quantum computers. And I will talk about that, about the evolution towards quantum safe computer and internet security. And I will talk also about a complementary topic, the safety. So with quantum computers, we will have communication of quantum data. And I'll talk about the safety of the quantum data communications.
cher cyber-CNI, pôle d'excellence région Bretagne. Au revoir et à la prochaine.